So, I'm going to talk to you about complexity. So, you're all enjoying the subject. We're going to be talking about math and stuff you all like. Actually, no. We're just going to look at some code and discuss copy and write, what it is, how it works, how you're actually using it with or without your knowledge when you're using the standard library. And finally, we're going to discuss the need for a modify keyword that is still in the process of getting into the language. But first, let's talk about something you probably already know. Well, I hope you already know it, but it's always good to remind yourself of it. I'm going to create a variable x, which is an integer, of value 0. And with that variable x, I'm going to declare another variable y, which also is an integer. And I want to modify my y variable by adding it 1. When I print x and y, I end up with 0 and 1. And of course, I have those values. That's the way we expect integers to work, and that's the way they work in any language I can think of. This here is called value semantics. It means whenever I'm modifying my y variables, I'm modifying y and only y. I'm not reflecting some side effect elsewhere in my code. Types like integers that provide value semantics are called value types. In Swift, value types are structs and enums. And as you might guess it, the last one missing is classes, and classes are reference type. They work pretty much the opposite way. Whenever I create a variable that is a reference type, I'm creating a pointer to something in the memory. And when I'm duplicating it, I'm duplicating only the pointer and not the memory. So whenever I'm modifying y, I'm modifying the memory beneath it. And that way I'm modifying x and y the same way. Swift is a bit peculiar as a language because it provides value semantics for types that we are not used to have, that are not used to have value semantics in other languages. For example, if we look at arrays, it's pretty common for us to think about it as value types in Swift, but in many other languages, these are reference type. And let's see how it works. How can Swift provide these value semantics? Because the tricky part is that whenever your type is using an amount of space that is variable, such as when you have a collection such as an array, you need to store it in the memory and use a pointer to interact with it. So how can we provide value semantics with something that is class-bound in a way? So let's see how it works in practice. So we're creating our variable x, which is an array, and so we're creating a pointer to the memory. And whenever I'm duplicating it in my y variable, I'm duplicating only the pointer, and both point at the same memory space. But whenever I want to modify my y variable, I want to keep value semantics here. So I need to make sure I don't modify x, and to do that, I need to copy and write. So I duplicate the storage used by my array and modify y along on the side of it, so I don't affect my x variable. So let's take a quick summary of what we've just seen here. In Swift, you have structs, class, and enums. Structs and enums are value types, and classes are reference type. Copy and write is the technique we use to provide value semantics to a class, to a type that is class-bound, because it needs, in the example of array, to have a variable memory size. And well, most of the Swift collection you can think of that provide value semantics rely on the same principle. But I've said I'm going to talk about performances, so let's look at performances. Here I'm having a vector structure, which is 3 integers. And I'm going to measure the time it takes for my vector function to complete. This function is quite simple, actually. It just returns its argument. You could say it does nothing, but actually, since in Swift, arguments are passed by copy and not by reference, when we're measuring the time it takes for this function to complete, we're actually getting a pretty good idea of the time it takes for the program to duplicate a vector struct. The value in itself is not really interesting, but we're going to compare it to other value because it only reflects the time it took to my computer in a certain configuration to run it. But here we have 500 nanoseconds. But what if we were to use a struct that were much more complicated than our vector struct? Here is an example of a struct from a project I worked a few years back on. And it's quite classic for an iOS project. The specific is not really interesting, but as you can see, you have many properties from something you can retrieve from a JSON, for example. And when we measure it, we can see that it takes more time to run it. And okay, so the more complex a struct is, the more time it takes to duplicate it. A fair question would be, how long does it take to duplicate a class? If we take the same data structure and instead of a struct we're going to use a class, it takes less time. This is a bit surprising, but we'll see later on why it makes sense. And once again, I'm going to show you a benefit of copy and write, is that if we were to implement a copy and write version of our struct, we would have the same time, we would take about the same time to copy it as it would take for a class. So let's try to make sense of what we've just seen. Whenever I'm duplicating a struct, I'm duplicating all of its content. So I'm taking my ID, topics, headline, highlight, and copying it. But whenever I do this using a class, actually, I'm not duplicating memory. I'm only duplicating the pointer to the memory. So I need to duplicate this pointer, which is pretty much the size of an integer, which is quite fast to copy. But there are some more operations to be done. For example, we need to update the reference count of our object. That's why it takes a bit more time than simply copying an int. So let's look at the number we've come up with when measuring for different types. We can see that classes tend to be much faster than structs whenever you have something a bit complicated to duplicate. But whenever you want to choose between a struct and a class, the only thing you should worry about is semantics. If you want value semantics or reference semantics. That's why if you want to have a better optimization and it takes less time to duplicate your argument and you have value semantics, that's when you want to use copy and write, for example, in your code. Also be careful not to want to use copy and write on everything in your project because it's going to bring a lot of complexity. And also, as you can see, if your structs are pretty simple, it's pretty much useless. You wouldn't want to implement a copy and write version of an integer. It doesn't make any sense. So, I've talked a lot about the benefits of copy and write. Let's see how we can implement it. We're going to take this simple struct, which is a vector once again, and try to implement a copy and write version of it. We're going to look at how it worked when we were using arrays and try to learn from it. When we had two variables of an array, there were two pointers pointing at the same memory space. So this is shouting class. At some point, we are going to use a class, and it is what we want to share the data between the two instances. So let's define a class. We're going to call it storage, and use it to keep our data, x, y, z, that are doubled. This class is going to come with two initializers, one with the properties and one with another storage to duplicate it. And both those initializers are going to print out whether we're initializing with property or with copy for us to really understand what's going on when we're using them. But more on that later. Let's go back to our struct and use our storage now. We create a private variable with a storage, and if we want to expose the X variable, we just need to create a computed variable. So the getter is actually quite simple. I just need to read the value in the storage and return it. But whenever I want to modify my X variable, I need to be careful because two instances of my core vector can point to the same memory space once again. So I need to copy and write, right? I duplicate the storage and modify it. This seems quite nice. But whenever I run these simple lines of code, I'm creating the vector, which prints out init with properties, which means I'm creating a storage. And when I'm modifying it, I'm duplicating the storage because, well, that's how we implemented it to be. But it might not seem a big deal here because we're only duplicating 3 integers. But if we were to have this implementation for your arrays, it would mean as long as you want to add one element, you would have to duplicate the array first. So adding an element to a 1,000 element array would take a crazy amount of time for the work we're doing. So we might need to fine-tune this implementation and make sure we're not duplicating the storage if we don't need to. Fortunately for us, Swift comes with a pretty handy function for that. This function is called isNown-uniquely referenced, and it returns true or false. True if the object we're passing, its reference count is 1. And in plain English, it means if we are the only one using it. If we are the only one using it, we can just modify things in place. And if we are not the only one using it, well, at this point, we have no choice. We just need to duplicate the storage, then do a modification. So this is how you do copy and write. As you can see, it's not that hard to understand once you've seen it once, but it's still a lot of complexity because here it's a lot of code just to give one X variable. We still have to do this for other variables, and you might have some work to implement it in your custom use case. Now let's see about what are the risks of using copy and write and how we can prevent the performance loss that comes with it. I'm going to define a class plane, which is a plane in space. And it's defined by an orthogonal vector, which is an instance of my copy and write vector that of before. For some reason, I've decided that I'm also going to provide a vector variable, which is pretty much only an alias to my orthogonal vector. This can be useful for one or two reasons I can think of, whether I want the inside of my class to use one naming and the outside of it to use a different naming, but it's kind of far-fetched. But one really frequent example is that I want my plain class to conform to a protocol that requires a vector variable. Then I just have to create this vector computed variable. Once again, here in the getter and the setter, we're going to print get and set in order to really understand what's going on. And let's create a function called set plain X vector component to value, which is going to set the X component of the vector to a value, because we are that good at naming. And let's use it in a simple case. We're creating a plane and setting the X component to a value which is 1. As expected, when I'm creating my plane, I'm creating a copy and write vector 3D, which prints out init with properties. But whenever I'm modifying it, it prints out get, init with copy, and set. What's that about? Well, let's see in detail. my setPlane vector component, well, it's really long. I shouldn't have named it that way. So my function is going to call the vector getter, because it's all it knows. Actually, it's a computed variable. It has a getter and a setter. So if I want to get the value, I need to call the getter. So the plane returns the vector, and it's actually a copy of it. But now I'm modifying it. So we had two instances of the same vector sharing the same storage, so I need to duplicate my storage. When I'm done mutating it, I can return from the setter of the x variable, and now I can finally call the setter of my vector variable to replace by the new value. So this is why we had to duplicate the storage. And once again, it seemed like not a big deal because it's a vector. Okay, it's 3 integers. But with an array, big problems. But how can we do that? Because our computed variable only has a get and a set. Well, the answer actually would be to use a keyword called modify that is not yet publicly released in the Swift language. Well, not officially released, but it's publicly available with an underscore before it. And what this accessor does is that you can, well, like a getter or setter implementation, you can do whatever the hell you want with it. But at some point, you have to call yield and yield something that is a curve vector 3D. This yielding means we're giving to the caller a way to modify things in place in order to avoid duplicating my value. Let's see that in a schematic. So my function this time is going to call the modify accessor, and the modify accessor is going to yield the vector. So now we can do our modification in place. We don't need to worry, it's the only copy of it. Once the modification is done, we return from the setter, and finally we doesn't do anything else than modifying the X component. We can return from the yielding, and finally return from the modify accessor. So this way we can avoid duplicating our storage, which is a big deal once again. And if you thought that this example was a bit far-fetched and you would never use something like this in your code, actually you might be using it also when you use property wrappers. Property wrappers heavily relies on computed variables, and not all of them, but most of them are using a variable stored and doing some work when you get the variable, then returning the variable and doing some work before setting it and then setting it. But it's the same issue actually. We're going to duplicate the variable at some point, mutate it, and then set it back. So we might need also here to implement our modify keyword. Once again, this is really only a problem if you're using it for something that is copy and write. But since the standard library use it for pretty much all collection you can think of, it's quite often actually. One last example for the road would be that if you have an enum and you have two cases sharing an array of integer in each cases, if you want to access the array because you know it's there, whatever the case is, and well, once again, you're going to use this pattern of creating a computed variable. And here again, you might run into performance issues. Finally, to finish, I want to show you an example that shows that providing a modify accessor is not that simple. In the example I've shown you, we were only aliasing something really simple. But if you were to, for example, want to add a modify keyword to the first element of a collection, you have to think about a lot of crazy complicated case. You have to wonder whether or not your collection is empty and do something about it. And even this implementation, which is quite nasty, you might run into issues because it doesn't take into account that what you're using is copy and write, once again. So if you want to modify an array that shares its storage with another array, you're going to run into trouble by yielding something that's not his in the first place. But that's not the main concern here. So, what should you remember from this talk? Computed variables are often something we use in Swift, and they might run you into trouble with optimization. Because if you use them with something that is copy and write, you might need to implement this modify keyword. I'm going to put that there because it's never repeated enough. Whenever you want to choose between a struct, enum, or class, you need to choose because you want value semantics or reference semantics. It's never about performances. And one final advice, which is valuable not only about copy and write. Whenever you're doing some optimization, you need to benchmark your code because you never know what the change you're doing can reflect elsewhere. You might be focused on some part of the code, but the global overview can be actually not good for you to implement, for example, copy and write or any other optimization. If you want to go deeper to the subject, here's a few links. So the stream from thread about the modify accessor, which is taken from the example of modifying the first element of an array, which is like already crazy complex, but not good enough. And 3 videos from Ben Cohen, John S. Weiss, and Corey Benfield. I think they all work at Apple, where they talk about copy and write or the modify keyword or the link between those two. And that's it for me. Thank you.
Good. So if you have questions, nobody doing copy and write manually? I mean, it's actually, yeah.
I think you look at to improve the performance in your application. Do you notice, do you benchmark the result, and do you notice edge performance improvement?
Actually, I never used it in production because I never had to improve the performance of my software to that extent. But I looked at it because it was a curiosity for me. But well, so I cannot answer and saying I saw big performance changes. But the people, Corey Benfield and John S. Weiss, I talked about giving a talk, used it in Swift NIO, if I'm correct. So I guess it does affect at some point. It's pretty useful at some point, yes.
About the modify keyword, so it's actually available with underscore. Will it like be available at some point as a public real like advice API?
Yeah, I'm pretty sure. Well, the aim of it is to become public at some point. Actually, Ben Cohen talks about it in his talks. So they created this modify keyword to make it available, but I can only speak for what I understand of it, but I wouldn't expect it to be available, officially available, unless until maybe Swift 6 or something like that.
You mentioned like we should use semantic type or otherwise only when it makes sense actually. And you said just important is to benchmark them. What tool and how would you benchmark those? What tool do you actually use to do benchmarking?
I'm not sure I understood the question.
What tool do you use to benchmark what do you advise people to use for benchmarking?
Well, I use Xcode, but you have to use profiling, I guess. There's well, I don't really know actually. I guess there is plenty more possibilities. But I think if you start with profiling and you go all the way there, you're pretty set already, to my opinion, at least.
So, Denis, is there a risk for your code mintability and complexity to implement your own copy and write?
Yeah, definitely, because well, whenever you're adding some complexity, you had a risk. You had a risk whether you're working in teams or whether you're working with your future selves that's going to look at the code and say, "What did you do?" But it's well. At least like any optimization, it takes some looking into, some benchmarking, and really, I'm going to say also some documentation, because you can't expect to write that code and say, okay, everyone can understand it, and we'll see.
Okay, and any use case where you would need to implement your own copy and write, or maybe a rule of thumb to do this?
I guess a good idea to know whether or not you want to use copy and write is whenever you're profiling your program, if you see that it takes a crazy amount of time for your program to instantiate structs that are still the same every time, you might need to use copy and write. For example, I don't know, if I were to use something really complex, such as my vector, but really complex, and I see every time I'm modifying a variable, I need to reinstantiate all of it, that means we're going to waste time here. But once again, benchmark before doing it.
So you spend a lot of time with instruments, right?
Actually, not even close. I spent a lot of time on the Swift forums and looking at some video from other conferences and learning by playing with it in the playground. But since I never had to run it in production, I never had to go to the extent of really looking into it with instruments, actually.
Okay. Any question?
No, it's all right. Just curiosity. How many of you are using like instruments to do benchmarking, like at least once a week? once a month. Yeah. Once in a lifetime. Okay. Thank you very much. So.
Thank you.